Hey, nice to meet you. My name's Alicia, and I'm here from Shopify Engineering. I want to talk to you today about feature stores and their role in data quality assurance. This topic is close to my heart because I'm a senior data developer on the machine learning platform team, but also, right now, I'm also the project lead of the data quality monitoring project for Feature Store. I wish I could be there today, but unfortunately, I'm based in Amsterdam, and the time zones just don't quite align. So instead, if you have any questions or follow-up comments, please contact me using the information I provide at the end of this presentation. I would be really interested to hear what you think. So let's go over what we'll talk about today. First, I'll share our philosophy around feature stores and how we design them to support good data science. Next, I'll go into the concepts and underlying technical implementation. Finally, I'll give you a sneak peek into our current data quality monitoring project. So let's start with the obvious. Why does this matter? I like to start with a scenario that people find familiar. So if you have trouble following the conceptual scenario, please feel free to use the illustrative one as a metaphor. Imagine that you and your team want to create a new machine learning model. You know your project requirements and your success criteria. So all that's left is to go out and find some features. If you're lucky, your data platform has a lot of really appealing looking options. However, you have to be careful and try them out, because unfortunately, you don't always get what you expect. It can be tough to navigate through data sources, but it can be even tougher to understand what they mean. For example, how is the feature being constructed? Is the pipeline being maintained? Is the quality being monitored? What are you going to get if you actually pull from this feature? This can be a little bit risky if you're considering it as an upstream dependency for your model. So it involves a lot of thought and trust. As a result, you and your team might decide to make your own features. That way you know what you're going to get. This means that you'll be creating your own data pipelines, which is frankly a lot of work. And consider also that you have to define your feature and figure out the concept based on the context of the data, which you may or may not know much about. So do consider that this doesn't free you fully from the quality consideration. Finally, let's be frank. Is this how you want to spend your time? You got this really meaty project, and this is an extremely lengthy way, or potentially lengthy way, to get there. And even in the future, you still have maintenance concerns if you own your pipeline. So this is not a risk-free scenario either. This places you in a bit of a conundrum. On one hand, you can use pre-made features without the work and hopefully relying on the experts who best understand the data. On the other hand, you now have an upstream dependency and you're at risk if anything breaks. On the other hand, you can make your own features and own your own data pipeline. But the downsides are extra work for your team, not just now, but into the future with maintenance and potentially duplicative work. Consider this from an organizational perspective. If you and your team want this feature, what's the likelihood that one of the other teams want this feature? Even worse, well, not worse. The first one's not so bad, but consider a worse scenario where you're both constructing the same feature. Are you defining it the same way? This could be kind of risky and honestly lead to a lot of confusion down the road. At Shopify, we aim to achieve a better approach with the feature store. Our philosophy promotes mediated data sharing with a feature store as a data broker. That way, we can ensure consistent infrastructural support and data maintenance for the features registered with our store. This is how we see our role in promoting quality data science. First, we support consistent feature definitions. By making it easy for domain experts to share their features with others, we promote the use of features that are designed by the people who are closest to the data, who understand the underlying dynamics. Furthermore, we make it more likely for other people to find the gold standard features rather than try to construct their own. That way, we hope to reduce duplication of features and instead promote the use of our gold standard features across the board. This should ideally reduce the amount of time that data scientists spend creating new features from scratch. Now, instead, they can focus on building their model, iterating with different sets of features to see what provides the best results. Finally, from a feature lineage perspective, This is beneficial to be able to understand how models and data relate. For engineers, we can better track these dependencies and identify who we need to contact if anything goes down. So now that we've talked about our philosophy and what we see as our role, let's talk about how our feature store is defined and how we implement it from a technical perspective. Panneau is named after panoramics, which is the French name for get-a-fix if you know the Asterix project. Panoramics provides a steady supply of strength-building potion for his fellow villagers. Panneau, the feature store, supplies a steady stream of features to strengthen our downstream models. If you're familiar with the concepts below, it's probably because you recognize the work put out by Feast. Feast is an open source feature store library/framework that we collaborate with closely, and Panneau is based on this work. Let me go over the concepts because I really want to make sure you can follow the following slides. A feature store is simply a registry of features. These features are defined in the feature store and stored as time series records to maintain event state. Consider, for example, the feature number of orders for a given store. This obviously changes over time. By storing this as a time series record, we're able to retrieve the accurate value for this feature at any given point in time. Another way we might retrieve features is by the grouping of entities. I said that weird, so let me restate this. Consider that there may be multiple features around a store. Number of orders, number of customers, days since being created. These are all about a store. The concept store is thus an entity. This is the logical concept that groups the features. We can have 0 or more entities associated with a feature. Another way to group features, but for a substantially different reason, is the feature view. The way that the feature view is defined is that someone who wishes to provide features to the feature store defines the schema for a feature view, composed of 1 or more features. The feature view is an abstraction over the data set that these features are drawn from. This data set is, let me stop there. So the point is the feature view has features associated by the shared association in a data set and is provided to the feature store. I want to make that distinction clear because the feature service is what's registered by people who use features, who want to use a set of features for the machine learning pipeline, experimentation, etc. This set of features are pulled from 1 or more feature views and are associated because of this usage. I wanted to make this very clear, so here's a diagram. A feature service pulls features from different feature views. These feature views are associated with data sets that are in our data sources. You may notice that there are multiple data sources in here. So one feature view per source, but multiple sources that these features are being pulled from. Using Feast's point-in-time joins and entity-based joins, we are able to abstract away the complexity of doing these joins correctly from the user. So the user specifies the features and general guidelines around these features, e.g. time range, and we manage the joins and extractions under the hood. Now that we've clarified that, let's talk a little bit about the data flow. Panneau is integrated with multiple batch and streaming sources at Shopify. The streaming sources write directly to our offline and online store, whereas the batch sources write only to the offline store. The offline store and online store are simply data repositories optimized for different tasks. The offline store is optimized for historical batch querying, whereas the online store provides the most recent data in a low-latent manner. So the data from the offline store is regularly materialized to the online store to make sure these stores are eventually consistent. When people want to use features, we've tried to make this as standard as possible across a number of scenarios. Our machine learning pipelines are set up to pull data from Pano's feature services. Ad hoc users can also experiment with features using our API. And then online inference cases operate the same as machine learning pipelines, except they provide a flag so that we know to pull from the online store rather than the offline store. Now that we've talked a bit about our feature store as it is, let's talk about what our feature store is becoming. So by this, I'm giving you a sneak peek into our work in progress on data quality monitoring. Let's talk about what data quality is. To start, we want to know the data exists. So that is our schema. We have 3 categories, and schema is our first category. Schema is simply that the data set that feature view is associated with exists and has the features registered in the feature view. Furthermore, these features should have the type in the data set that the feature view says they have. If this schema is not accurate, we don't allow it in the registry. A more interesting problem is when the underlying data set changes or is removed. So we need to be able to alert quickly and effectively, especially because downstream feature services depend on this feature view. So that is where a beneficial aspect of the lineage comes in. You'll see this theme repeated across all 3 categories. The next category we consider is data freshness. Our data sets have specific SLO expectations. We need to flag the feature providers if their underlying data set fails these expectations. We also need to let the feature services know if one or more of their features are affected by a freshness violation. This could be important if their model is dependent on highly fresh data. Finally, data value validations. Beyond simply type, some features have more specific guidelines that we should be able to assert when pulling the data. For example, we might expect a numerical value lies within a certain range. Perhaps we want to assert that it is not negative, or that there's a specific range that is permitted, 0 to 10, 1 to 100, whatever. If it's a string, perhaps it is expected to meet a given format or a specific set of valid values. Whatever this is, we need to be able to define it on a feature and provide the same monitoring over these validations as we have for the others. For feature services, they should also be alerted if there are upstream violations. They can provide their own validations further down at the point of consumption. We're focusing on feature views for these validations because that is what's shared in the feature store. So if we look at these 3 aspects of data quality from a user perspective, here's the main objectives we have. For feature providers, we need to provide an easy way for them to define the schema over their feature view. By schema here, I mean both the actual schema that we currently have and the value validations that we're adding in. They should be able to modify these schemas as need be. For example, say a set of strings now has a new valid value. This should be an easy change. For feature providers, they should also have access to our alerting and monitoring systems. Furthermore, when they're alerted, they should be provided with sufficient information to help them debug and investigate an issue. For feature users, with slightly different aspects, they should be able to look at a feature schema as well, so they can understand the underlying properties of the feature. Furthermore, they should be able to see a history of that feature's quality events. They would want to know how fresh is this feature? Does it typically meet its expectations? Does it regularly have validation successes or failures on specific value validation rules? That way, they can make an informed choice before adding the feature to their feature service. When they have registered a feature in their feature service, they'll get access to upstream alerts. That way, if anything happens to a feature, if any of the quality expectations fail, they'll be notified. This way, they can take action. Finally, data changes. We recognize this, and we referred to this earlier with the modifications of a schema. This might not always cause a problem, but we should give feature users notice. So we need a way to relay these updates if the feature definition has changed or become deprecated. I would love to talk to you about all the work we've been doing to explore and analyze different technical implementations to solve these problems. However, we're not ready to publicize this. Please stay tuned, and hopefully we'll have a follow-up talk sometime about this. In the meanwhile, let me share with you some key takeaways. First, data sharing is great. It's great to see data scientists help each other out, especially when one has context that they can share and put into practice to aid others. Let's make it easy to do this well and build in safeguards to help protect our users. I like to think we're helping our providers too by supporting the monitoring efforts with our shared infrastructure. Talk to your data scientists. They are working on this kind of stuff every day, and they have valuable insights that can inform what you should implement with regards to your feature store, what place it can have in their day-to-day workflow. Next, integration is key. It does not matter if your feature store is designed magnificently if people cannot integrate it with either their downstream machine learning pipelines or upstream data sources. Its place in the ecosystem matters for usage and to be able to benefit the most people. Finally, be user-obsessed. Because data quality issues affect people, it is a human problem as well as a technical one. No one wants data quality problems, but as long as the real world continues to change, and that change is reflected in the technical world, data will not meet all expectations. Let's help our users solve data quality issues by providing them with the information and support they need to investigate the underlying problems. Finally, thank you on behalf of the panel team for having us in the opportunity to present today. If you have any follow-up questions, feel free to contact me at the link below. And in the meanwhile, I hope you enjoy a little bit of time to have a coffee break and even maybe a little bit of cake before the next presentation. Enjoy the rest of the conference and hope to hear from you. Have a great day.